Hello, this is the Tepid Coder. Today I want to talk about function pointers, and I think the way I want to introduce it is going to be with callback functions, but I also want to talk about it with how it relates to classes. So let's make a basic test case here. I'm going to do, thinking here for a second. First of all, I want to talk about the syntax for a function pointer. Normally when you make a function, you have like return type, you have your function name, parentheses, and you have the types of the arguments, so some type, type 1, name 1, right? And you have type 2, name 2, dot dot. So what you can also do, if this is your function body, is you can declare this function to use it somewhere else. You could say r, called name, you could say t1, t1, t2, dot dot, all your types without the names. And we've seen that with the function signatures we've used, especially with the DLLs that I was making recently. But if you want to make a function pointer, what you can do is you can say r, you'll say name, use the same format here, t1, sorry, t2, whatever. But you're going to wrap this in parentheses and put an asterisk in front of it. That means it is a function pointer. This is going to be a variable that points to a function which returns type r and takes type 1, type 2, and some other types as arguments, right? So let's show an example of that real quick. I'm going to make a function, let's call it, I don't know, print something. This would be an easy case. It doesn't take any arguments, doesn't return anything. All it's going to do is say something, right? It's going to print something with a line break. Now, what I can do is I can make a function pointer in the same way. I'm going to say return type is void. Okay, and inside of parentheses, with a little asterisk here to say it's a pointer, I want to call it fn print something. So fn for function. And the parameter it takes is void. Okay, now I can say this equals print something. Oops, not something. There we go. And I can just call it. Say print something. Call it just like a function. And that should print something. So let's try and do that. So ++ test SCP, I showed test. And it works. Now, something else you can do here, which is kind of nice, is you can make an array of functions. So before, it was a pointer to a function, right? Now it's an array of pointers to functions that return void and take void as an argument. So what I could do is I could say void print something else. Okay, and this one, we're going to say print out something else, right? With a line break. And now, just like with any other array, you can do open curly brace, close curly brace, and you can make an array of things you want to assign all at once with commas like this. So I'm going to say print something else. And here, this would be the, what do I say? I'm going to call this function array at this point. So function array. Let's type it all out. Okay, so function array. I might even say fnary, because it's kind of redundant, but whatever. We're going to call the 0th function in the array, which is still going to print something. Okay, let's do that. Okay, line 17, we made a mistake here. Expected comma or semicolon. So I forget, yeah, right here I forgot a semicolon, because I'm ending this statement right here. Okay. Test, still print something. If I wanted to print the second one, I could obviously just do this, right? It'll work. Something and something else. Another thing I could do at this point is I could say, for like say SDI 0, SDI less than size of fn array function array. I can say divided by size of, and it's going to be a function which takes a void argument and returns void. Oops, man. I cannot type today either. That's a little bit hard to read right there. I'll make this a little bit easier in a second. So it's this divided by this. size of is of this thing over here. So we have void. Okay, there we go. So it is a pointer to a function which returns void and takes void as an argument. Let's wrap that in parentheses just in case. Okay, and then every single time the loop runs, let's increment. Okay. So remember, if we have something like the size of a variable, that size is going to be the size in bytes of this whole variable. Now, the size in bytes is the number of elements we have, 2, times the size of whatever these function pointers are, which just for a regular function pointer, it's going to be 4 bytes in x86, it'd be 8 bytes in x64. Alright, so it's going to hit end here, and this one will end here. Okay. And for each time we loop, we're going to print the current function. Alright. So, let's see, size in bytes divided by the size of each element is going to give the number of elements. So from 0 to the number of elements, minus 1, we're going to loop, because once it hits the number of elements, it stops. So it's going to print element 0 and element 1. Okay. Expected primary expression before void. Is it not like that? Think about that for a second. What if it's not going to let me do the size of a function pointer? I mean, I would think that would work, right? So I have... I want to count these real quick. I'll say I have 1, 2, 3, 2, 3, 2, 1, 0. So I did align them properly. But why would it complain about that? Maybe I can't have those extra parentheses. Let's try that real quick. Yeah, that's better. Okay, so I printed something. It should print both, though. So the size of the whole thing, which has 2 elements, divided by the size of each function pointer, starts at 0, goes up by 1 each time. Oh, what am I doing? I stuck the plus plus in here. I mean, I could do that and just remove it here. That'll work as well. Jeez. It just prints both functions. Okay. That was silly. I don't know why I did that. Anyway. So yeah. It prints both functions. That's kind of cool, though. You can have like an array of things that'll happen all at once. But that's not particularly useful in this case. But it's interesting you can do that. You might use something like this if you have something like a language you're making, and you compile things down into opcodes. Each opcode would be an index of a function, or the index of a function array, I mean. So if I want to call like the first function, I could say, you know, call function array 0. If I wanted to call maybe, say you have a function like assigns values, a function called assignment, right? Maybe that's 0. Maybe you have a function that adds 2 values, that's function 1. You have a function that subtracts 2 values, function 2. You could do that, and you could index into here, and call each one based on a function pointer. And what you could even do then is you could make it so that whatever functions you want to use are the ones you assign. So maybe you can have it work differently depending on context somehow. So that's kind of neat. Anyway, the reason I bring this up isn't for making your own interpreted language, though it would perhaps work for that. Or for interpreting something, if you're making like a emulator. Instead, the reason I bring this up is it's useful to be able to have function pointers for what's called a callback function. So you can imagine I have a function that takes a function as an argument. So I'm going to make a new function. I'm going to call it print your thing. And inside here, what I'm going to do is I'm going to say, take a function which returns nothing and accepts nothing, and it's going to be called fn, call me. So we have an argument called fn call me. And this function is going to say fn call me. It's going to call it. So this function is going to call whatever function you pass to it. So if I say print your thing, and I pass it print something, that will work because it accepts a function pointer which returns nothing, a void, and accepts nothing. And print something, I defined it such that it returns nothing and accepts nothing. So it has the same function signature, right? The type is a void pointer to a function. Sorry, try that again. It's a pointer to a function which returns void and accepts void. That's the signature for this, right? The fact it's called print something is irrelevant. It could be this as well. It takes the same parameter and returns the same thing. So either of those would satisfy this right here, right? It's expecting that. As long as it satisfies this for the function signature, it'll work. So let's do that. And there you go, something. It prints something. Now, there are functions that you'll see which expect callback functions. A good one I can think of is a sorting function, right? There's a sorting algorithm. There's something called qsort, which would be quicksort. That comes with C libraries. It might be in standard lib.h. Let's see. I'm not sure. Standard lib.h. And what this will do is it should take a pointer to some block of memory, and it should take, I think, probably the size of the element to iterate through, and it should take some kind of callback function which tells the caller, which is qsort, it tells it what to do with each element. So I'm actually going to look real quick at the C qsort documentation here. Let's look at, geez, I just want the actual, well, here's something on MSDN, this will work. So yeah, let's pull this over here. So it takes a void pointer, which could be any type of pointer. Doesn't matter what the element type is. Okay, number, I'm guessing that's the number of elements. Width is probably the size of each element, and here's your comparison function. So let's take this function signature right here for qsort. It even tells us what this is. Yeah, okay. Start of the array, element size in elements, and the element size in bytes. Okay. Compares two elements, returns a value, specifies a relationship. So is it less than, is it equal, whatever. So let's see, does it expect just less than? I'm guessing that's all it needs. Okay, so less than 0. Then it's less than, if it's 0, they're the same. Okay, well that's pretty easy. If I sort two integers, that means I can subtract them. And if it subtracts and it results less than 0, then it's going to be the case that element 1 is less than element 2. I'll show it in a second. So let's do this. Qsort right here, just so we can look at it. What I want to do, oh geez, I'm gonna make this a bit smaller so it'll still be on the same screen hopefully. Okay, I'm gonna assign an array here with values. I'm gonna call it UI8array values equals, let's give it some numbers. I'm gonna say 17, 12, 0. In fact, I'm gonna make this a signed array. It's gonna be signed 8-bit integer array. Let's do negative 13, 99, 215, 12. I already have 12. Let's do a, I don't know, a 2. We can have another 12, it doesn't matter. Whatever. Case being that we are having a array of things we want to sort, and we're going to sort them so that inside the array, the smallest one's going to be first. It'll be, looks like negative 13, then 0, then 2, then 12, then 12 again, then 17, then 99, 215. So when we access the array here, and we say we want position 0, it's going to give us this instead of this once it's sorted, right? That's what that's for. So the base, it's saying, give us a pointer to the first element, right? Which is just this. I could also say it's position 0 and I could reference it, right? But essentially it's just this. It's the same thing. So number, that was the number of elements in the set, which is going to be size of this divided by size of an int 8t, which is just 1 byte each, right? So I don't really need to put that, but I'm going to, just for the sake of making it generic, right? If I change the type here, as we're an int 16t, so it's assigned 16-bit integer, it'd be 2 bytes each. So the size of would be wrong. Oops, I need to do that. And this would be wrong because it's 2 bytes each. What I need it to be is the number of elements. So the size of each element divided into the total size in bytes will give me the number of elements. Okay, and the width of each element is just size of int 8t, which is 1 again. Okay, and then we have a comparison function. So now, this is where it gets interesting. I'll say fn compare signed 8-bit, say, 8-bit integers, right? That's our function. Oops, come on. Okay, now we need to make that function. That function, let's look at the signature again. It needs to return an integer. It needs to take 2 constant void pointers. So let's make it that. It needs to return an integer like this. The calling convention needs to be C declaration, which should be the default that's used. So let's say that, just because C declaration, ECL. Okay. And it's going to take a const void pointer and another const void pointer. Now, we have to give these names so we can work with them. So I'm going to call them A and B. Or I guess I could even call them, you know, left and right. Now what's going to happen is, it's going to go through this array we have here, and it's going to look at every 2 elements that are next to each other. Well, I guess it doesn't have to be next to each other, but it's going to look at each 2 elements that it wants to check, and it's going to ask you, if you have this and this, which one's smaller? That's basically what you're going to tell. So if this one's on the left, this one's on the right, you want to know which one's smaller. I'm going to say, since these are both integers, I'm going to return left minus right. What that's going to do is, if left is less than right, let's give an example here. Let's say left is 1 and right is 2. I wrote R for some reason, so 2. So it's going to say 1 minus 2 is negative 1. Well, in that case, if you look over here, it should be less than 0 if element 1 is less than element 2. And if you're looking right here, it says element 1, comma element 2. So element 1 is the left. So the one on the left, if it's less than the one on the right, it should be less than 0. And that'll happen if we subtract them. Okay, let's look at the next case. If they're the same, what happens? Well, if they're the same, so left equals right. In that case, what if we have 1 and 1, right? That would be 1 minus 1 is 0. Okay. And does that satisfy the condition? Well, if they're equivalent, it should return 0. So yes. So the next condition would be right is greater than, or sorry, left is greater than right. So let's reverse it and say we have a, I don't know, a 2 and a 1 this time. So 2 minus 1 equals 1, which is greater than 0. And if we look over here, where is it? Here, greater than 0. So that's right, it'll be greater than 0. And that'll hold for any of these numbers. So this should be a valid comparison function. So we can call this. And what I want to do is I actually want to loop through this array here. Oops. Start at 0. Come on. I is less than. I can actually just copy this again. Number of elements. I'll do that. Okay. And for each one, I want to print out the value. So standard out, we're going to say value. All right, I'll make it even more explicit what I'm doing here. This position, whatever the position is currently, maybe PRI, let's say U64, and the value is actually going to be a PRI I8, it's an 8-bit signed integer. And like usual, I'm going to do my static cast thing, just because I like to be able to see at a glance what's happening. I'm going to say static cast unt4t. Okay. And we're going to say STI. And then over here we're going to say I8 array values position STI. Okay. Let's recompile this now. So, what do we have here? Invalid use of const void. Right. I was treating this like it was a signed 8-bit integer because I knew that's what I was working with. But really, what we have here are const void pointers. A void pointer is a typeless pointer. So it's the same size as any other pointer. All pointers are going to be like 8 bytes in 64-bit applications. They're going to be 4 bytes in 32-bit applications. Unless it's a class pointer, that's a bit different. I can maybe talk about that, but not right now. Anyway, so we have a long pointer to some void value, left and right. What I need to do to actually compare these is make them a real type. So the way I do that is I'm going to cast it into a pointer I can use. I'm going to say it is an int8t pointer. I'm going to say I8 left. In fact, it's a long pointer to an assigned 8-bit integer. I'm going to say it equals, I have to cast it, int 8t pointer to LPB left. So if I have a pointer, void pointer, and I want to make it a different type of pointer, this kind, I just cast it like this. So that should work. Okay, we're going to do the same thing for right here. Okay, now I can actually compare these. So LP I8 left, I'm dereferencing it because right now it points to 1. I want the actual signed 8-bit integer at this address, so I'm dereferencing it with an asterisk, right? I'll do the same thing over here by dereferencing this one. So LP I8 right. Now let's see if it compiles. It's going to go plain. So nearing of 215 to right. It's too big of a value. I can't actually put that in there. So remember, the range of assigned 8-bit integer is going to be 2 to the power of 7, or you could say 2 to the power of 8 over 2. That's the max negative value it could be, right? 2 to the power of 7. Up to, it's going to be 2 to the power of 8 over 2 minus 1, or 2 to the power of 7 minus 1, which is going to be negative 128 to positive 127 inclusive. And this value 215 is too large for that. So I'll make it the max possible value you can put in there, 127. So it's not going to complain about that. Okay, what else do we have? So line 74 expected this. Okay, let's see why that is. Line 74. I think, yeah, I didn't put in type, so it doesn't know how to use PRI UCT4. Okay, now we're good. Negative 13, 0, 2, 12, 12 again, 17, 99, 127. So it's sorted now. So that's how that works. Now, there's some other things I can do to make a little bit of this easier. I'm going to say, instead of having to dereference this, let's actually use the reference type I was talking about in the previous video. And I'm going to say it equals the address of this thing. So right now, we're casting the void pointer into a signed 8-bit integer pointer, and I'm dereferencing it to let this reference it. So if I wanted to, at this point, I could actually say I8 left equals something, like 10. I could actually modify the value. Except I really couldn't because it's a const pointer. But if it weren't a const, it would actually let me do that. And really, technically, since I'm working with a const pointer and comparing it, the compiler should have complained at me, because I'm converting between a const void and a non-const pointer. That's actually incorrect. It should be a const reference, and the cast I did should have been a const signed 8-bit integer. In this case now, it's no longer a pointer to that. I should be able to do this, right? Let's try and compile that. It still works, see? That's a bit, I think, easier to read once you're doing this. You can treat it just like you defined it here, as if you did like int 8t, you know, I8 left, right? Equals 10, or 18. You know, if I define it like that, it reads just the same way, which is nice. This part up here, a little bit more confusing to read, but I don't know. It's up to you if you want to use that kind of format. Something else I can do to make things a little bit easier is like right here, I have all this garbage. I can define a constant integer value, or even constant size t value, let's say. I'm going to say array element count, right? I'm going to say it equals all of this. And this can be constant because this size right here is being defined right here when I create the code. It's defined in the code, so it's never going to change. So it's fine to call that constant. That means this value can never change in the code either. So I can't like update this at some point and say constant thing plus plus or something. So I can just use this now instead. It's more clear what I'm trying to do, right? That shows my intention. This will leave the same because it's the size of the element that I'm using in the array. Okay. And anything else I care about here? Right, I can use the same variable over here because I want to know the number of elements to loop through. So I'll do it here. Okay. And it works just the same. Alright, so now I've gone through that. In the next video I do, I want to talk about other ways you can do these callback functions. In C++, you can do things called lambdas. So instead of actually defining the function and then referencing the function here, like this, I can use a lambda, and I could actually put the function body right here and put stuff in it. That kind of makes things a bit easier, because you can define things right where you're using them. So, for now, I'm going to leave it at this. I will catch you again in the next video with the C++ way of doing these things. If anyone has any feedback they'd like to give, or any criticisms, anything they'd like me to expound upon, please feel free to leave that in the comments. Like and subscribe, all that fun stuff. And thanks for watching. I'll catch you later.